Hi everyone, Mrs. V here, and today we are going to be learning about the technique of mass spectrometry. We are going to learn how to interpret a mass spectrum and get some information from it about the structure of an organic molecule. So let's get right on with it and start learning. Once you've isolated a natural substance and you want to make it in the laboratory, the first thing you need to do is determine its structure. That way you will know what your target molecule actually is, and that's going to allow you to design a synthesis. There are a range of instrumental analyses available, and each one is going to provide a piece of the puzzle of what that structure actually is. Mass spectrometry can provide information about the molar mass, which atoms are present, and also some information about position of functional groups. Infrared spectroscopy can show you which functional groups are present. And nuclear magnetic resonance spectroscopy can show you the structure of the carbon backbone and also gives you detail about where the different hydrogen atoms are in the molecule. It can also tell you the position of some of the more highly electronegative atoms. In this tutorial, we will learn to interpret a mass spectrum to gather some clues about the structure of an organic compound. Mass spectrometry weighs the molecule, so it can give you the molar mass. It can provide information about which elements and functional groups are present and also their likely positions in the molecule. The instrument used is the mass spectrometer. Now you only need a tiny sample for this technique, and this is good because this technique is what we call a destructive technique. You are never getting that sample back. The mass spectrometer has three main components. We need something to vaporize and ionize molecules in the sample and produce a stream of charged particles. That's this part of the machine here. We need something that is actually going to deflect the charged particles by producing magnetic field. That's the magnet here. And we need something to actually detect the charged particles after they've been deflected by the magnet. This is the detector screen here. The first step is ionization. That just means making the molecule charged. This can be achieved by bombarding the sample with high energy electrons or bombarding it with ionized molecules. Electron bombardment just means firing high energy electrons at the molecule in the hope of hitting an electron and knocking it out of the molecule. This is going to give the molecule a positive charge. Firing high energy electrons at a molecule also tends to break the molecule into pieces. Various covalent bonds can be broken, and the shattered pieces of the molecule are called fragments. Some fragments will be charged, while others will be radicals. You remember a radical is simply an atom or group of atoms that has an unpaired electron. Generally in a fragmentation we always produce one charged fragment and one radical fragment. The next step is the acceleration stage. The charged fragments will accelerate as they pass between the charged plate in the spectrometer. An electromagnet creates a magnetic field that deflects the charged particles. You can adjust the machine so that the particles don't end up hitting the walls here or here. The higher mass particles, because they have greater inertia, don't actually veer off course very much. So the higher mass particles are going to end up in this section of the detector screen. The lower mass particles are deflected off course much more. The lightest particles will hit over here. This is how the particles are separated according to their masses. The particles crash into a detector screen. The charge on the particles causes an electric current when the particle hits the screen, and this allows the spectrometer to count the particle and record its mass according to where it hit on the screen. The graph produced is called a mass spectrum. It's a plot of percentage abundance versus mass to charge ratio, which is what M/Z stands for. Most of the particles will have a charge of +1, which means their mass to charge ratio will just tell you their mass. But some might have a +2 charge if 2 electrons were knocked out of the molecule. This is the exception rather than the rule. The peak for these will be at half the actual mass, but it'll be fairly small and insignificant. The largest peak is called the base peak. This is the tallest peak. This is assigned a percentage abundance of 100, and all other peaks are compared to this peak. A really useful piece of information we get from the mass spectrum is the molar mass of the compound. This is determined from the peak that's furthest to the right. There might be a tiny peak just to its right that's caused by carbon-13 isotopes, but this tiny peak can be ignored. The peak that's furthest to the right is called the molecular ion peak, and it corresponds to the mass of the entire molecule. So this gives us the molar mass of the compound. The other peaks correspond to fragmentation and can give us some information about the location or functional groups or polar bonds. You need to have a fair idea of the structure of the molecule from other forms of spectroscopy to identify all the fragments. The mass spectrum alone does not reveal the structure of the organic compound, but it does provide some pieces of the puzzle. Let's learn to identify some of the main features in the mass spectrum. Here we have two mass spectra, pentane 2-one and pentane 3-one, and we're going to learn to identify each of the peaks that we see from the fragmentation and also the molecular ion peak. Compare the mass spectra below and explain the various peaks. The mass spectrum is being used here to distinguish between two isomers of pentanone, C5H10O. We have pentane 2-one and pentane 3-one. Both have molecular ion peak at a mass to charge ratio of 86. This corresponds to the molar mass. So 5 carbons, 10 hydrogens and 1 oxygen adds up to 86.15 grams per mole. If we took that to the nearest unit, we would see that that matched the 86 of the molecular ion peak. Let's look at the fragmentation of pentane 2-one. If we look at the structure of the molecule, we can work out places where this molecule might fragment. Let's have a look at a fragmentation next to the carbonyl carbon. This is going to produce 2 possible fragments. Let's calculate what their molar masses would be. So in the first fragment we have 2 carbons, 3 hydrogens and 1 oxygen. It's going to give us a molar mass of 43.05. We see a peak of 43 on the mass spectrum. Our second fragment has 3 carbons and 7 hydrogens. Also 43, this would explain why that peak was so large, had such a large abundance. We have 2 separate fragments here that contribute to that peak. Let's have a look at a different fragmentation. What if the fragmentation occurred on the other side of the carbonyl carbon? This will produce 2 fragments. The first of these has 1 carbon and 3 hydrogens. This is going to give us a molar mass of 15.04. We can see we do have a tiny peak here, suggesting that's not a very likely fragmentation. The second fragment has 4 carbons, 7 hydrogens and 1 oxygen. That's going to give us 71.11. And again, we see this peak appear in the mass spectrum. Let's compare this with the fragmentation of pentane 3-one. Let's again look at the fragmentation next to the carbonyl group. This will produce 2 fragments. The first fragment has 2 carbons and 5 hydrogens. This is going to give us a molar mass of 29.07. And here we see the peak. The second fragment has 3 carbons, 5 hydrogens and an oxygen. That's going to give us 57.08. Here we see the peak at 57. So you can see that the 2 different isomers produce different fragments for the same molecular ion peak, which allows us to identify which of those 2 isomers we have. Your turn now. I want you to pause the video and try and explain the peaks that are observed in this mass spectrum of ethyl ethanoate. We'll be back with the answer in a minute. Let's try and fragment this either side of the carbonyl carbon. Let's try fragmenting it here first. What will we get? The first fragment has 2 carbons, 3 hydrogens and an oxygen. This is going to give us 43.05. Can we find that peak? Here we have, that's a very large peak. The second fragment, 2 carbons, 5 hydrogens and an oxygen. That's going to give us 45.07. Here we see that peak. Now why would that peak be so much smaller? Well, it's quite likely that a fragment can be broken up into further fragments, so it may just be that this particular fragment is not overly stable. Let's have a look at a different fragmentation. Let's try the fragmentation on the other side of the carbonyl carbon. 2 fragments produced. First fragment, 1 carbon, 3 hydrogens, 15.03. Can we find a peak there? Yes, we can. Second fragment, 3 carbons, 2 oxygens, 5 hydrogens, This gives us 73.08. Can we find a peak there? Oh, quite a small one. However, this fragment is likely to break up further. What about if the molecule fragments here? So we produce these two fragments. First fragment, 2 carbons, 2 oxygens, 3 hydrogens. It's going to give us 43.05. And we've already noted that peak at 43. The second fragment, 2 carbons, 5 hydrogens. It's going to give you 29.07. And here is your peak. That's all for today. I hope you found this video useful, and if so, please give it a like and also subscribe to my channel, watch some more videos, keep on learning and enjoying this wonderful subject of chemistry. I'm going to see you guys in the next video.